Is it work?
So, for the next session, we have a focus on software supply chain with Luis Sorrero, and this is our for this year's ECW, and we spent the morning with our nice session. If you could not attend, don't hesitate to watch the recording, and besides that, I will give the floor to Luis for his presentation.
Does it work like this? Okay. So, welcome, audience. Je veux... parce que je suis... Okay, I'm going to speak in English, okay? I'm Luis Sorrero. I'm doing the PhD thesis on code ledger. It's about tracking the software artifacts from the origins to the final product. I'm on the second year, and now I'm going to talk about a little, the small part that I've already done of the research. So, let's start with a question. How do I know if I can trust this piece of software? Okay, this piece of software might be one that I'm using, or might be one that I'm providing for others. So this is the question: is this software trustable? Okay. In order to answer that, we need to look at the software supply chain. That's where software is made with many small pieces. But when we look at the software supply chain, we see that's not very easy. Because first, most 90% of our software is made of free software. You have free software components. Sometimes you know, sometimes you don't even know that your partner has used them inside your software. And there are over 7 million free and open source software components, and they're all made in different places, with different forges, different people, different institutions, in different world regions. So it's kind of complicated to know exactly how each piece of software came to be inside your software. And when we try to answer that question, we see that in the state of the art, the literature, they usually define the two, they divide in two areas, okay? One, it's the focus is on the dependency graphs. This software depends on this, this, and this, and then try to see if there is any vulnerability inside all those dependencies. And the other focus is on the day-to-day operations, the operations stage, where they try to see how attacks work, what they do, and this kind of operation-based attacks. But there is no unified way of looking at the problem, so we are trying to look at that. And the current goal is try to come with a threat assessment for all elements of the software supply chain. Okay, what would be the use case for that? One is this: given that we know you have the software supply chain information, okay, we want to know how vulnerable is my product? Can I estimate the level of threat it's the level of threat that that it provides? Is it safe? Is it vulnerable? Is it compromised? And if it is, where can I look in the software supply chain to mitigate that problem? Okay. And the other use case is this: given that I know the state of the supply chain, and some part of it is inside my network, for instance, I can see, this is vulnerable, this is vulnerable, this is vulnerable. It doesn't mean it's compromised, it means it's vulnerable. But if I know that's vulnerable, there is a higher chance of being compromised. So I can focus my intrusion detection systems and monitoring on those components. Okay, so far we have come with this we call log model. Okay, it identifies the main components of the software supply chain, like the hosts, transformers, software artifacts, and also we define a threat model. Okay, it's a simple one. We adopt a pessimistic view. So if something is not safe, there's a higher chance of being vulnerable. Or if something is malicious, that means that it can inject things. And then we try to see how it propagates down the software supply chain, okay? We capture the history of the software supply chain in a property graph. And you try to come up with an algorithm to apply the roles so that you can know in the whole supply chain how each element is vulnerable or not vulnerable or malicious. Here is a little bit difficult to read, but there is no need to read. Just to give you an example, this is a very, if you look at a real software supply chain, you have thousands of nodes with many components. But if you take just a small part of the software supply chain that's written here, we have two examples here. On the left-hand side, we have one. These are the products that we are interested in. Okay, there are two software products. And suppose that we already ship those products. Okay, we are already shipping that to customers. And then somebody on the team says, hey, there is a CVE that says that there are some vulnerabilities that were discovered in some components. Can you check if we are safe? And then, yes, if you have the log model, you could identify that these three components were vulnerable, initially vulnerable, okay? And we apply the threat propagation rules. And you see that, no, our product is still safe because of the rules of propagation. There are no higher risk of them being vulnerable. On the other hand, on the right side, it's about the same scenario. We are already shipping the product, but then somebody says, hey, we know that there was a malicious software component that's been found in the wild. Can you check it? And then we see, oh, that malicious component is this one. It's an low persistent library. But when we apply the propagation rules, we see that there is a high risk that it's already infected this host, which already infected the build environment, which infected the transformer, which contaminated the two software artifacts. And here there is another thing. They were published to another host. But this host here, it's not executing this software. It's just published for distribution. So the probability of that host being compromised because of this is almost none. So in this case, we might try to contact the host that was compromised, look at our network environment inside the enterprise, and try to contact the host to remove that software that we were distributing. So there are two examples of it at work. And we have published it, and there was not published. We have submitted and had the paper accepted for this log model. And that's it. If you have any questions.
Difficult exercise.
Yeah.
In real cases, the graph may be very huge, very big. It's easy to make the propagation of the rules and update.
It's greedy.
Yes.
Because it's monotonic. So basically one pass in the graph. And basically it's okay. Okay, the first instance of the algorithm is recursive. So basically we might backtrack several times on same nodes. But this design, because it's monotonic the property on nodes are monotonic, so you cannot go below the level you reach. So because it's monotonic, then a flooding algorithm starting from the entry point of the graph will allow us to do it in one pass, basically. We just need to rework the algorithm.
Yeah.
If some part,
I'll let you answer.
if some part it's compromised, is it easy to mitigate the problem or something like that? We have to remove this
well-
part of the code, or we have to take another instance who are not compromised, something like that.
I think that it depends on the kind of compromise that happens. For instance, if you have a host that is compromised, let me backtrack here. Yeah, if you have a host that is compromised, we take the pessimistic view that if it is possible to inject software, it is injecting software. So we might try to get all those components from other hosts that wasn't compromised. But it goes like this. It depends on the kind of.
But it's always easy to know where is the modification or compromise in the code.
Yeah, on the cases where it's vulnerable on the left hand side, you can try to replace the code or.
There are forensic methodology. For instance, there are teams like Sébastien Bardin teams at CEA that work on extracting footprints or evidence of tampering of binaries that are markers for malwares. And so, for instance, but it's costly to analyze the binary, so you cannot do it for all the supply chain. So one of the points with the work of Luis is that it can be, this kind of model can guide. For instance, you start with an assumption of a compromise on the build environment, and then you identify all the resources that are supposedly compromised, and then you mark them for analysis. You might end up not marking all the network, only the one that is related to this assumption. And thus it helps you to manage the priorities.
Because sometimes if you put some GitHub or something like that, some open source code, you may have the master seed, but we may have also fork something like that.
Yeah.
Sometimes I take one or another.
A part of this initial work was to identify, that's what he said a bit in the beginning. There are people that made a lot of effort about vulnerability propagation analysis, but basically with respect to read attacks on the supply chain, no automation, no reasoning, no support for reasoning. And so that's what was the motivation behind this work, is was to say, hey, let's first try to propose a model to integrate both views, and that's what okay, it's not that much, but basically we say to people, okay, why not combining both views? Basically, it's also a way to combine attack graphs, classical attack graphs, with dependency trees. It can be seen as like that. The tricky part was to have a selection of concepts, because if you want to type it inference rule, you need types. If you put too much of them, it's horrible. If you have too few, it's not.
It's missing.
And that was the tricky